Now that we have a basic understanding of atomic structure, we're going to go a little deeper. We understand that the nucleus is where the protons and neutrons are, and this region of space known as the electron cloud is where we find the electrons. But we want to know where exactly are those electrons within that region of space. And to determine where the electrons are, we need to understand the concept of energy. And energy in this course will be discussing in terms of work and heat. So energy is defined as the capacity to do work or transfer heat. And we'll represent work by the letter W and heat by the letter Q. And most of the time we'll be dealing with energy in the units of joules, which is equal to a kilogram times meter squared per second squared. Energy comes in two forms that you're probably familiar with: kinetic and potential. Kinetic energy is associated with an object's motion. So you can think of a rolling ball is a pretty common example. But it's not limited to tangible objects moving. We can talk about kinetic energy in the form of light, in the form of heat, or in the form of sound, are just a few examples. Potential energy, on the other hand, is associated with an object's position. So we can have gravitational potential energy. For example, this marker has some gravitational potential energy at this height, and at some lower height, it has a smaller gravitational potential energy. For our purposes in chemistry, we will be more interested in electrostatic potential energy, which is the amount of energy that is associated with two particles. Central to the discussion on energy is the first law of thermodynamics. It says that energy can neither be created nor destroyed. It can only be transferred from one form to another. So let's consider a rolling ball. If we roll this ball up over a mountain, say a small hill, as the ball is rolling up the side of the hill, its speed is decreasing. And so its motion is slowing, its kinetic energy is decreasing. As it climbs the hill, its potential energy is increasing. So we're transferring mainly kinetic energy initially to primarily potential energy at the top of this imaginary hill. If this ball were to travel down the other side now, it's taking potential energy and being transferred to primarily kinetic energy as the ball speeds up and decreases its altitude on the side of the mountain. Aside from looking at the conversion of energy from one form to another, such as kinetic to potential or vice versa, we can also study the transfer of energy between a system and surroundings. In chemistry, we define a system as a subset of material. It's the particles that we're studying, and these particles can be an individual atom, they could be molecules involved in a chemical reaction, or it could be a beaker of some material that's undergoing a phase change. And then the surroundings, on the other hand, will be everything else in the universe, anything that surrounds it. However, we're most often interested with the immediate surroundings. So maybe we're going to be looking at the air immediately surrounding some system, or a solvent such as water that a chemical reaction is taking place in. Those are all things that we can study the transfer of energy between. As we study energy transfer between a system and surroundings, we're going to be looking at internal energy, and specifically changes in internal energy, or a delta E. Now, the internal energy by itself is the sum total of kinetic and potential energy within a system. The change in internal energy will tell me whether or not my system has gained or lost energy. So we'll be looking at this idea where we have a final state and an initial state. And there are two scenarios that we could imagine. If we have internal energy on a y-axis, we could start at some low energy. We'll call that my initial point, and we could end at some final energy. To get to this higher energy level, energy must be put into my system. And so delta E here would be a positive value, greater than 0. The opposite scenario would be if we start at a higher level and end at a lower level. In this case, my system must have lost energy, so my delta E will be less than 0, or negative. We already introduced the idea of heat and work, and it turns out that the change in internal energy can be related to the heat lost or gained by the system and the work done on or by the system. Let's look at the specifics and how we define Q and W with respect to a system. So when a system gains heat, we define Q as positive. And when work is done on a system, we define W as positive. Now work is equal to minus P delta V, where P is pressure and delta V is changes in volume. So W will be positive when my volume gets smaller. Okay? So think about having to shrink down a balloon. That's going to be work done on the system, assuming that no air came out of that balloon. It would take work, you as the surroundings, to push and make that balloon smaller. On the other hand, when a system loses heat, we define that as Q being negative. And when a system does work, that is a negative work value. So again, with respect to work, I have an analogy that might be kind of a stretch, but imagine you're inside a balloon. You are now the system, and you are pushing out the walls of that balloon. It takes effort for you to do that, and so you are doing work to expand that balloon volume. Okay? So Q and W can be positive or negative depending on whether heat is lost or gained and work is done on or by the system. So it is very important that you understand the signs of Q and W and how that pertains to the sign of delta E, because that is what determines whether or not the energy has gone up or gone down in my system. I hope you found this video helpful in understanding energy and how we can look at changes in internal energy of a given system, and how those changes are related to the heat gained or lost by the system and the work done on or by the system. So make sure you understand the definitions and keep track of the signs, positive and negative, and let me know if you have any questions. Thanks for watching.